Good morning, engineering 2. Can you guys hear me? Yes, Rachel, thank you. All right, so let me start the class by sharing my screen. It seems to me like today in the morning when I wanted to start the class, I was like, oh shoot, I did not create the Zoom link. So that's probably why you guys didn't see it before, but I did it. So you just come to the regular class, you should see the link. I created it in the morning, but I usually create them over the weekends. And I do not make it like a recurrent event because there are things always something happening in the middle, and that's why I don't do it that way. Okay, so in terms of the lecture, we are going to be talking about manufacturing tolerances. Full sections you is actually going to be covered in the on Thursday, but this Thursday I will not be giving lecture and I will not be in the lab. So again, you guys most likely will have to work remotely, just like before. Um, I'm going to assign you two new homeworks, homework number 12 and homework number 13, all the way to the top. Okay, tolerances. What is tolerance? Well, before we start any of this, let me bring my camera and let's talk about what is a tolerance. This one, light. And let me get the flashlight. Okay, so every time that you guys draw something, you most likely will want you model it and you say, oh, it has a diameter of 1 inch. Or it has a hole here. It seems to me like it's about a 3/8 hole. It has a hole that is a 3/8, or it has a width that is about 1 inch, and so forth, right? When you go, you model it. Most likely, you model it perfect. So it is 1 inch, 1 inch, and we're gonna because you draw it in a model. The model will be 1.0000000 continue, right? Forever. Because it's a vector-based program. All these programs that you guys are using are vector-based program. But in reality, somebody is going to grab your drawings. Your manufacturer is going to grab your drawings. It is going to make a 1 inch. But guess what? To make it 1 inch, it's not going to be perfect. So when they go and they do it, they might make it slightly bigger. So let's say let's say they make it 1.10, slightly bigger. Or they can make it slightly smaller. Let's call it 0.990, right? Really close to 1, but none of them are right in the money. And again, it's because at the end of the day, somebody has to use tooling. And tooling, because also we got human error, things get not to happen as you expected. Nothing in the world is perfect, right? Especially you need to make this guy happen. You guys see the difference? If you guys were to create a bunch of them, you would have like a lower limit and an upper limit. Your lower limit is the smallest I can get and the bigger I can get. But there is a little range of what is acceptable for you in terms of function. This acceptable range is what we call a tolerance. Tolerance. How much leeway you give them, such that your part still functions correctly, but again, you want to give it as large as possible so it's easier for them to fabricate. It makes it cheaper. So you want to give this tolerance as large as possible to meet function. And let's actually start talking about it. There's a bunch of things that I need to go through. So there is no such a thing as exact dimension. Tolerance must be applied to all dimensions. Yes, everything that you get to draw, somebody will have to manufacture. You need to let them know what will be the leeway for them to make it happen. There are different ways of applying the tolerance. You can apply it as direct limits or as tolerance values. Direct limit pretty much telling me, you know what? The upper limit is this, the lower limit is this. This is what we call direct limit, directly to them. They don't have to do any math. The tolerances values, you can also go and give it to them as, I don't know, do 1.00 plus minus 0.01. Or you can do 1.00 plus 0.01 minus 0.02, right? Or you can do 1.00 plus 0.01 minus 0.00, right? So you can give it to them. This is the tolerance range. This is direct limit. Direct tolerance. I give it to them directly. These are not directly, right? In the direct limit, they don't have to calculate anything. It's already there. Okay, as geometric tolerance, yes. So if you guys continue, let's say you guys continue, there's another class that we teach here. In fact, the requirement for that class is engineering 2. Engineering 2. Engineering 2 is a requirement of the class to take a class that is called ETEC 34. ETEC, ETEC 34. ETEC 34. If you take this class, I will prepare you to get certified by the ASME GDTP. It's the American Society of Mechanical Engineers, Knowledge in Geometry, Dimension, and Tolerances Principles. Uh, it's a course that will prepare you to be able to design and manufacture parts for fabrication. Uh, so in fact, the skills that you get here, which is GDMT, let's call it Advanced Tolerance Principles, are things that are, if you guys remember, Livermore Lab comes and always look for people. Well, that's pretty much what they people that know GD&T. I've seen it. I've been here for about 2.5 years, and I noticed that that's pretty much the main skills that they're looking for. So again, if you go and you take the class and then you get certified by the ASME, then you guys are pretty much. I got in one student, he just got his certification, he just got hired. So really important skill. Again, you can do it through GD&T, which is another type of tolerance. We actually going to glance to it. Not right now. We just barely started. You can also put a note in the drawings. That's why you guys have your. If you guys look at your note, notes that you put on the drawings, and you guys have put so far since the beginning of the class. Or you guys probably remember something that says, unless otherwise specified, all dimensions should be plus minus 0.015, 15 thousandths. So this is the leeway. The one that I was telling you guys. And again, there should always be a leeway because in the drawings that you make, nothing will be perfect. The tolerance is pretty much telling your manufacturing personnel what is the upper limit and the lower limits that they can fabricate the part. It also controls the form of the part. If I want to have a part, and my part, you wanted to control its form, and it's saying how wavy, the tolerance, again, you can make it small, which we call it the lower limit, or you can make it big, which will be the upper limit. And again, it could be this size, it could be this size, it could be somewhere in the middle, right? Which is controlling the size from the upper limit to the lower limit. And again, this is the tolerance. The upper limit and the lower limit, they are actually controlling also the form. My part would actually come over here and have this shape. And as long as I'm within the lower limit and the upper limit, my part will be in spec. If I want my part crop, it looks like this. If I were to measure it, and if it's less than the lower limit and the upper limit, like we indicated it, my part will be in spec. So it's actually controlling your form as well, how wavy the part is. You can put it in the title block. I've seen it many times. If you guys remember, when you guys look at your block in your drawings, your drawing title block looks like this, and it has the border, and then it has a block, so King Delta College, da 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 da. And many manufacturing companies or mechanical companies, what they do, they have a kind of like disclaimer, and somewhere in the disclaimer right below it, it has the tolerance. All linear dimensions, all angular dimensions. They also put a profile tolerance, stuff that you will not learn what it is until you take the course. But again, it will be on the title block in itself. Unless otherwise specified, where a general tolerance note on a drawing includes angular tolerances, it applies to features shown at specified angles and at applied 90 degrees angles. So what it's telling you, if you go over here to the regular note that we do all the time, that it says, unless otherwise specified, actually this one doesn't say, it should have another note that says, unless otherwise specified, and then you have a note there that says all angular dimensions should be plus minus I don't know 1.0 degrees, something like that, right? You also have an angular, so if you were to have a part that looks like this, right? Let's make the box like that, something like that, and it has an angle. You are controlling you're making the dimension not by measuring here or from here to there, you're just measuring the angle. You will have a plus and minus on the angle. I mean that this guy could be here, we could be there, right? So let's call it 1 degree, a little bit bigger, less, 1 degree, a little bit more, right? Kind of like a variation in angle. So this angular tolerance will apply to any angular feature, and it will also apply to infer 90 degrees. You will not be dimensioning every 90. The 90, 90, 90 will take you forever. It's just saying, you know what, every surface that are perpendicular to each other, I have a discrepancy to 90 degrees, uh, discrepancy from 90 degrees as 1 degree, plus minus. 1 degree this way, to control the orientation between different planes, right? That's pretty much the note. That's what it's trying to tell you. So you have tolerances for linear dimensions, and you have tolerances for angular dimensions, and you guys have tolerance for geometric features. That's where this other class will come about, which is GBNT. Okay, let's go. Let's go and take a look at the tolerances. Let's learn how to read them. When I go and I tell you, hey, you have a unilateral equally distributed or unequally distributed. What does it mean? Okay, so what you guys see here, it is the examples that I told you guys before. The nominal size, sometimes called the design size. So if you guys were to look something in terms like a 1 inch or 2 inches, so you have a hole that is 1 inch diameter or a 3/4 diameter or so forth, the first number that you will see there will be the nominal size, or sometimes called the design size. Right next to it, the little plus and minus will be your tolerance. And again, I want you to think about it like a region where your part could be a little plus and minus, but your part could have form. Let me see, not this one. Your part could have form like a little region. Let's see the little region. This is what's the tolerance. And again, starting from coming over here, you have a lower limit and an upper limit. The tolerance is this guy, where it could have form and variation in size and form. It can increase size based on whatever is my upper and lower limit, and it could have a variation in form as long as I am within my upper and lower limit. Okay, let's call unilateral tolerance. What's a unilateral tolerance? This is what unilateral tolerance is. Okay, so that means that if I go and I tell you, hey, you know what? You have a hole. I'm going to make this kind of like three-dimensionally. Have a hole, and then you have a pin that's going to go inside of it. And let's say that this pin is, and I went and I measure it, and again I had a range because I went with the caliper, and my pin in reality will be like this, right? And I measure from here to there, and I measure from here to there. That one will define this point, kind of like the center of it. I measure from here to there, that one will define that point, and then you just continue. Eventually, I got the worst case condition of measuring my pin. In the worst case scenario, I found out that my pin, the maximum I could be, would be 1.00. Okay, so now I'm making a new part, and my new part, I need to ensure that this pin will always fit into this hole. Well, what I can do, I could say, you know what, I need to make sure that my hole will always be bigger than 1 all the time. That way I would always ensure that I will have a fitting condition. Doesn't matter what, it will always fit. So I'm going to say that this guy is going to be a diameter of 1.000, and I want to make it bigger, 0.010, always bigger, and nothing smaller. Nada. Because if it gets smaller, it will not fit. So, and in reality, you will also have a little allowance. And say, you know what? When I were to actually do it, and if you were to put the pin, let me redraw this guy. If you were to put the pin, there should be a little gap. And again, this is the tolerance for the pin, and this is the hole, and this is the tolerance for the hole, right? Little plus and minus. This is your tolerance. So always a little gap, right? To ensure that will always fit. In the one that I show you guys above, it has no, there is no gap because this is 1, and the worst case condition is going to be 1. So in reality, you will have to have an allowance. But in terms of what you guys are learning right now, a unilateral tolerance will always have a 0. It's telling you, you know what? Just go from the design size. You either always make it bigger, or make the hole, or make the pin always smaller. So let's say that this guy will be 1.00 minus 0.00 minus plus 00 minus 0.01. Telling you the pin will always get smaller, only smaller, right? So it will always fit, and the hole will always get bigger, only one direction. This is pretty much what I'm trying to tell you. And how do I identify I have a unilateral tolerance? Well, I will always have a 0, right? Because I'm only going in one direction from my design size. Unilateral tolerance allows part variation in one direction only from the nominal. You guys will notice that you guys have a 0, and you guys have a 0. You can have this guy in terms of length as well, right? That's how you know that you have a unilateral tolerance. Let's take a look at bilateral tolerance. I tell you, hey, you have a bilateral tolerance. What does that mean? When you guys have a bilateral tolerance, that means that you have bilateral change. It changes in two directions. So for example, again, I go back to the same example that we had before. This is my 1 inch, 1.00. And right now, it is my perfect condition. But in reality, if I were to, and again, this is my design set, right? 1.00. In reality, you will have a tolerance. It might get a little bit bigger. It might get a little bit smaller. If I were to do unilateral, that means I will have one of them because I will only move in one direction. Get rid of this. I will move only in one direction, either making a little bit smaller or making a little bit bigger. But when I have a bilateral, that means I go both directions, right? So I might go equally distributed. That means I'm going to go the same on both directions. Or I might do unequally distributed. When I go one direction a little bit larger than the other direction. So let's say equally distributed, this one equal, and this guy is unequal. Right? And how will you write it? Well, if I were to do equal distributed, equally bilateral, I know that the equally bilateral are going to be equally on both sides. So the way you will say plus and minus, and then you will call this guy, I don't know, 0.01. Okay? So 10 thousandths. That means I'm going to go up by 0.01 and smaller by 0.01. My tolerance is going to be equally on both directions. 0.01 up, 0.01 too, going down. If I were to do, let's call this one, if I were to do an unequal tolerance, that means that I'm going to go different errors. The size of my tolerance will go differently. So in this case, will be something like 1.00 plus 0.03 minus 0.01. Right, so I'm going a little bit, I'm giving them more leeway in terms of how it goes in one direction than the other direction. That's pretty much what it means. Okay, and again, this is kind of the same concept. You guys will notice that you have equally distributed, you go up and down equally, and unequally distributed, you have different directions of growing. Let's talk about upper limit and lower limit. So upper limit and lower limit. So upper limit, as the name implies, it is the biggest it can get or the smallest it can get. So if I were to draw this, I'm going to make a pin. This is a pin, and I'm just looking at the side. And if I were to look at the tolerance, right? Let's say that from here to here, this is the lower limit. This is the smallest I can get. And this guy here is the upper limit, which is the biggest I can get. And again, it doesn't really matter if I have a hole as well. I could do the same concept by hole. And I'm just looking at the hole sideways and cut it to the part. It's like if I were to have a hole that looks like this, and then I have the hole there, and then I just cut through it, and this is what I see once I cut through it. See if I can cut through it. If I were to cut through the hole, this is what I would see. And again, you guys also will have your lower limit, and you will have an upper limit, right? So the biggest I can get, the lowest I can get, the smallest I can get. All right. So let's read the definition. The upper limit is the equal to the nominal dimension plus the positive tolerance. So the biggest I can get, right? In this case, I got 1 plus minus. This is bilateral, equally distributed, and I'm moving up by 5,000, so 1.005. And the lower limit is the smallest I can get, which is equal to the nominal dimension minus the negative tolerance, if any. So the smallest I can get, 1 minus 0.005 or 0.95. The biggest, the smallest. So let's write those numbers down. So we already have some numbers. We'll put them here. 0.995 and 1.005 and 0.95. 0.95. Right? And then if you guys recall, I told you guys, if you guys were to just look in this little region, this is what we call a tolerance. Well, if you were to do this mathematically, in order to be able to find the tolerance, I will have to grab the upper limit and take away the lower limit. So upper limit minus lower limit will give me my tolerance. Okay? This in itself is a tolerance. It's telling you, for my design size, I'm going to go 30,000 up and 10,000 down. So my tolerance in here will be 0.04. And again, you can draw it, right? You can draw it up and down. You want to draw the one that I just did. You have two sides from here to there and from here to there. This guy, the biggest I can get will be 1.03. The smallest I can get is 0.99. And that way you can look at the tolerance, which is this one, and boom, done. Okay. Let's actually look at the next one. The tolerance again is the total allowable variation of the dimension is equal to the upper limit minus the lower limit, which is your tolerance. And the direct tolerance, direct limit is when I give it to you direct. I just go and I write it. Okay. You will always put the direct tolerance in order. You will put the lower limit on the bottom and the upper limit on the top, or the lower limit on the left and the upper limit on the right, like the example that you guys see here. You can do it horizontal or you can do it vertically. So, and again, remember that the lower limit is the smallest and the upper limit is the biggest. So we just put it that way. Make sure that the smallest bigger, smallest bigger, smallest biggest, smallest biggest, the smallest biggest. Always have that direction. The smallest, the biggest, the smallest, the biggest. Upper limit, lower limit. And again, you guys will notice there is no plus and minus anywhere because it's given to you directly. That's why it's called direct limits. Let's actually talk about how it would be on the drawing. So you want to put this on the drawing. How would you put it? You would put this on the drawing. So if you want to put this on the drawing, it's really simple. In metric system, it's really simple. Metric system, you just make sure, as before, when you're doing each dimensioning, there is no little zeros. And when you're doing a little plus and minus, you need to make sure that the number of decimal places match. Okay. For example, the one that is on the top, that one is direct limits. You guys will notice that the top and the bottom should match. So like this, not like this. The next one is bilateral, equally distributed. So you will put it with the same number of the decimal places. So 3 decimal places, 3 decimal places. The next one, it is unilateral tolerance, because it only goes one side. And again, you make sure you always put the same number of decimal places. Even if you were to do a angular tolerance, we'll still do the same. Make sure you have the same number of decimal places. So for each tolerance is not too bad, but if you were to do millimeter tolerance, then it would be a little bit harder. For millimeter tolerance, there are more rules. And the rules will apply depending on what type of tolerance I'm using. So you guys remember we have unilateral, we have bilateral, and we have direct limits. I tell you directly. So if you were to do direct limits, you will just make sure that you have 25.45, 25.00, the same number of decimal places. That one's not too bad. It's similar as before. Top and bottom should have the same number of decimal places. For unilateral and bilateral, it's a little bit different. So keep in mind that when you are doing millimeter dimensions, when you have a whole number, the whole number will not have any trailing values. I don't know if you guys remember, I said, you know what, in your dimensioning, in this right, you guys can see it right there. If you have anything that is whole values, like this 36, or like that 15, or like that 12, you will not call out 12.00. In metric dimensions, you will just call it 50 millimeters, 36 millimeters. Well, when you have unilateral tolerance, that 0 is also counts like I guess a whole value. I'm not sure if that would make sense. But you want to do 0.00. You just call the 0. And also keep in mind that it doesn't have a little minus. I don't go 32 minus 0.00, just 32, 0. No plus, no minus, just 0. And then you call out the tolerance for the other direction, right? You got unilateral, so it only goes one direction. If you were to do bilateral, what you will have, remember you will have a leading zeros like in every metric, right? Anything that is less than 1, you will have a leading zero, just like this one. And then you will have the plus and minus. It's because you're doing bilateral, right? Up and down. And again, your number of millimeters will not have 0.00. So it's a little bit more complex than the ones that were before. So for example, you guys going to compare both of them. So I can compare both of them. So for example, if I were to do unilateral, let's do inch system, and let's do metric system. If I were to do unilateral means only one direction. That means that in each I will just say 1 point. I don't know. Let's do 32 since it's the one that is there. 32 inches is kind of like too much length, but let's call it that I do. If I were to unilateral, I will do 32.000. Actually, no. Let's do it in this. 32.00 plus 0.00 minus 0.02. Right? That will be the inch. 2 decimal places here, 2 decimal places here and there. And if I were to do it in metric, that 32 will not have the leading zeros because it's a whole number. Then the 0 on the top will also be considered a whole number. And the 0.02, that one will remain the same. But I will have a leading zero because I have metric. It's a little bit more complex. If I were to have a bilateral, and this is going both directions, that means one a little bit up and a little bit down. In each system, you will do 32.00 plus 0.25, and again, no leading zeros on the inch, minus 0.10. Right? Same number of decimal places here, top and bottom. No leading zeros. Same number of decimal places. In metric system, well, I will have that 32 still there. It's a long because it's considered a full number. And then I will have plus 0.25. And again, I have the leading zero because this is metric. And then minus 0.10. Slightly different. And then if I were to do direct limit, well, this one will be the closest similar. So it will be 25.45 and 25.00. And if you were to do it in metric, it will be the same, 25.45, 25.00. Right. So slightly difference for unilateral and bilateral, direct limit, pretty much the same. Again, same concept in terms of, pretty much the same. Okay. Let's talk about production tolerances. Oh, the time stop. The class is already started. Okay, so most likely what I will do, I will continue talking about this in the class, in the lab, going over the production tolerance. I think it will be beneficial for me to talk about it in the class, in the lab, and then we can talk about the homework also, which is your tolerance homework. Let's call it. I'm gonna let you go home 1 minute early. Good afternoon, engineering 2. Let's talk about what you guys should have met, what should have watched, you should have become master of. Hopefully. Okay. And you watch the lecture, and again, if you didn't, it's okay. Don't worry about it. When things get manufactured, somebody else it's actually not just a model. Somebody has to go to somebody has to weld. Somebody has to use the milling machine. Somebody has to do the lathe machine. Right now, we are doing things at 3D printing as well, but nothing is perfect. I mean, in your model, it's going to be perfect. 0.000, right? 1.0000. But in reality, things are having imperfections. So for that reason, and because things are not perfect, we usually have certain leeway of how things are going to be manufactured, such that things can fit together and behave the way you want them to behave. So let's say that I have, I don't know, let's have this guy that looks like this. And in this case, I kind of like I have a height, right? Sometimes I like it when I put on my calculator. Let's say that I have a height for this slot. It's this one. Does it look like it? Yeah, pretty much, right? Let's suppose I have a height and I go and I tell it in my drawing, I model it, and I say, you know what, this guy here has to be, I don't know, half an inch, right? And I model it to half an inch, and then somebody needs to ensure that it meets my requirement. On top? Okay, that little requirements, that little leeway, where my part will have a variance, is what we call it a tolerance. So I'm going to come over here and I'm going to give it a little leeway, right? Call it like this. The little leeway will contain what we call it the lower limit and what we call it the upper limit. The bigger I can get and the smaller I can get. If I came up to the upper limit, like this, that means that it literally has to be perfect. It cannot have any form variation. Because if I were to make it any type of variation, any type of this, it will overpass my upper limit. And then my part will not function. Usually go and give it the leeway, right? Now, if I were to go to the lower limit, say my part came up to be that size. If I were to go this size, it will have a lot of leeway. Again, sorry for the resolution. It will have a lot of leeway for it to go up and down. You guys see it? All right. So what is this leeway? How do we get this leeway? Well, this leeway, which we call it tolerance, it is a region. And in this case, it's a region for dimensional tolerances. D for dimensional tolerance. I usually teach a class next semester, right? Which is the G, D, and T class. It stands for geometric, dimensional, and tolerances. You guys taking this class, you guys meet the requirement. Okay. That class that I teach is called E-Tech 34, and it's pretty much is advanced mechanical drafting. And I usually, when I'm done with that class, I usually get serious, prepared to take the ASME, write it down, ASME GDTP certification exam. Right. And what I have seen people is that after they got it down, they put it on the resume, and they have work in Little Lab, Lockheed Martin, they have work in Sandia Lab. Okay, because not a lot of people get certified. It's a hard class. I'm not going to tell you it's going to be easy. If I'm going to introduce you to GD and things, most likely when we come back to the spring break. Okay. Okay. The D, yes. Thank you. This guy has been coming on. Wait, put it there. The D is what you guys are going to learn today. But you guys have seen this in your notes. Somewhere in your notes, in the bottom of the corner, you guys have something that says notes. Unless otherwise specified. All linear dimensions, plus, minus, most likely you will see something like this. Plus, minus 2 feet out of an inch. Right? Like you've seen that before? That is pretty much the D on GD and T. For all your dimensions, I'm going to allow for manufacturing to have a lower limit and an upper limit. You get to live anywhere in between. It will allow you for form variation and for size. Is it? Okay. Now, the first one that you guys should know is the tolerance. The tolerance is a region. It's the difference between the upper limit, and the lower limit. Okay? So again, it's just this little guy right there. If I were to go and I were to come over here and have things that are assembled now, let's say that I'm going to have that's going to look like this. I'm going to grab this guy and I'm going to put it inside of it. Let's say that this guy is 1.000. And again, it can also go down. It can go up and it can go down. All of them, right? In my case, I want to make sure that that piece can go inside of it 1,000 times. Whatever, it doesn't matter what it is. I have to guarantee that this thing is going to go inside of it. How do I guarantee that it will go inside of it? Well, I have for this, in case we're going to call it a hole, it has a lower limit and it has an upper limit. Are we good? I'm going to look at the worst mating condition. In this case, will be the lower limit. Yes? The worst mating condition. And then what I'm going to do when I go and I put my slot, I am going to make it such that the worst meeting condition, when in this case my shaft, hold like a shaft, hold like a hole, when my shaft is the biggest, it will still fit into the hole. And this little portion right here, we're going to call it allowance, which stands for the tightest fit. Okay? Now, sometimes what we do is this little region, we call it different names. Okay? Let's talk about the names how we call it. But again, the whole idea is to come up with function and get my dimensions in such a way that if I have 1,000 parts and 1,000 assemblies, they all can be assembled, and I can guarantee assembly. Okay? All right. So how we do this? I'm going to grab that shaft and come over here, and I am going to be looking at the base dimension. It's only 1.00. I'm going to grab that guy and I'm going to zoom in. Okay? Let's call that the baseline dimension. Let's call it the zero line. It's just this line right here. Okay? Okay? Assuming that is my perfect size, and it's 1.00000. Okay? Now, sometimes as I'm defining my tolerance zone, I can define it in one direction, yes, or I can define it another direction. In other words, I can look at my shaft and say, you know what? For example, in this case, I can say, you know what? I am going to make it, I don't know, let's make this guy, I don't know, 0.01. I'm going to make this guy 1, which is the lower limit, minus 0.01, that will give me somewhere here. And I just want to make sure that we always go that direction. So that means I will get to the base dimension and I only go down. That makes sense? So again, I'm just looking at that line, and my tolerance zone, this is the zero line. My tolerance zone will be here. That means that my part can only get smaller if it's like that, right? And if I were to go it on the top, that means that my part can only get bigger. You guys see it? So I'm playing with my tolerance. This guy, we call it unilateral, equally distributed tolerance. Why is it unilateral? Because it only goes one direction, right? Why is it equally distributed? Actually, no, it's not equally distributed. Actually, yes, it's equally distributed. Let's just call it unilateral tolerance. Equally distributed is when you distribute it equally in both directions. For example, I'm going to put another line somewhere here, and I'm going to put the same shaft, and I'm going to allow it to go up and down, and whatever is on the top has to be on the bottom. This is how you guys have the plus 0.015 minus 0.015. If I were to have a shaft that is 1 inch, sorry for the camera. If I were to have a shaft that's 1 inch, and if I have the zero line and I go up, 15 down, and down, 15 down, we call it equally distributed. Because here, it's equally distributed in both, right? This guy also we call it bilateral. What's it called bilateral? Because I go on both sides, right? This guy is unilateral, because I only go one side. Does that make sense? So again, this guy could be, I don't know, 1.00, 0.989. I only went 1 and below. That makes sense? And this guy, I don't know, this guy could be 1.3, let's not make it that big. 1.120, 1.000, right? Which means I only made it bigger. Are we good? Okay, I can also have bilateral and equally distributed. That I distribute it in different ranges. So let's see, an equally distributed will be maybe if I have a shaft that will look like this. And again, this is my baseline, and I go up and down other different ranges, which look like this. How would that be? I don't know, 1.150, 0.999. See? I went from the 1, and then I went 150 down, right? 150,000 up, and 1,000 down. Are we good? Okay. This guy, we call it bilateral, and we call it unequally distributed. right? I distribute it differently. Okay, review. The smallest size is called the lower limit. The biggest size is called the upper limit. The difference between them is the region where your thing needs to be manufactured. This is what we call it the tolerance, the dimensional tolerance, which controls two things, the size and it controls the form. Your part needs to be manufactured somewhere in between. When my part is at the biggest I can get, it has to be perfect, right? When my part as the smallest I can get, they will have, it will allow for form variation. I mean, my thing can go a little bit quicker, right? Like as small as it can be, right? This tolerance zone can be distributed in different directions. I can distribute it unilateral. That means I only make my shaft bigger, or I could make it my shaft only make smaller. I can make equally distributed like the way that you guys have it in your general notes, typically, or you guys could have it unequally distributed. Are we good? I mean, bilateral, unequally distributed. No? Now, where do they get these numbers? The Professor Calona, where do you get 15,000? You just making that thing up? No. I'll tell you where we get those ones. Over here. And I'm telling you because not too long from now, we're going to start fitting things together. And we need to start fresh from tolerances so we can start fitting things together. And they're going to behave the way we are expecting them to behave. Right? Again, this is what you guys call it. Sometimes we call it base size. Sometimes we call it nominal size. Sometimes we call it design size. This is the 1 or the 2 or the 0.375, which is the 3/8, or maybe the 0.5. The yellow ones is what we call it the design size. The blue, it is indirectly calling the tolerance zone. For example, here it's telling me plus and minus 5,000. Right? That means I went from my design size. I can go up by 5,000, down by 5,000. What is my total tolerance zone? 0.010. Right? 10,000. Does that make sense? What you guys will notice here, this is the equally distributed, and this one is the unequally distributed. You can have unilateral tolerance. That means you only go one direction. You can have bilateral tolerance, the one that is equally distributed, and the one that is unequally distributed. And remember, the tolerance zone is the region. So you do one minus the other. You can also call them directly. Like I believe I gave you all your examples. Right? Instead of give you plus and minus, it will directly tell you what is your upper and your lower limit. Now, in terms of inches and millimeter drawings, let's call it, this is an extension of what you guys should already know, which was this, right? You guys remember this? I think I covered it somewhere in the lecture. I told you that you're not supposed to have zeros in the front. Yes. A dimension is expressed to the same number of decimal places at its tolerances. So if you guys want to come over here, you will notice that if I have 0.750, 0.748, I don't switch them. If I have my tolerance, which is this guy, that it has 3 decimal places, my design size should have 3 decimal places. When I go and I tell you in your drawing plus minus 15 tau, 0.015, that's 3 decimal places. That means everywhere in your drawing should have 3 decimal places, unless otherwise specified. When would I specify something that is different than 15 tau? It's most likely because it has a specific function. Right? What kind of function, Professor? Maybe my thing is going to have this type of it. So let me show you the type of it. You guys will notice here, here I have a pin. See the pin? And if I were to flip this, you will see a little hole right there. Okay? Okay. This fit right here is what we call it an interference fit. That means that in order for me to grab the pin and insert it into there, I have to mess with temperatures. This guy here, this pin, it is so fused and it's as strong as a well, if not stronger. How do I make this happen? I come over here and I make a shaft bigger that are hole. Again, this is my hole. This is the biggest I can get. This is the smallest I can get from here to there, right? This is my shaft. Now, if you guys want to look at this, can this pin fit into this little hole? One, right? One. So what do I do to that hole? I heat it up. I heat it up with that thermal expansion. It goes a little bit, right? And then I grab that pin and hammer it in. Right? That thing will never go nowhere. In fact, you guys can try it. The only way that I can take this one out is most likely destroy it. Right? And it never go nowhere. Okay. In order for me to be able to get that type of fit, I need to pull out my bazookas, and I most likely will have to have a special type of fit, right? Which we'll talk about it later. Right now, just tolerance. Okay? In millimeter tolerances, it has a couple more rules. You can have unilateral tolerances. Again, it only goes one direction. You guys will notice that it has a big O zero. No point, no nothing. 32 millimeters, 0. And then this one has a leading 0. So it's a little bit more tricky. You guys have a cheat sheet, I believe, somewhere in there. That you should have this in front of you. Right? In case you guys, if I ever make you do drawings that are millimeters. What's up? You can also have bilateral. You can also have direct limits. And again, the ones that I like the most is the direct limits. Now, this is what I covered last time. If you don't want the lecture, what's the lecture? So, these are my quick review. I have a lecture, man. Go on. Okay, so I give you guys a note in your drawings that you guys usually put at the bottom corner, and it says notes only otherwise specified plus minus 15,000. Yes or yes? You remember that number, right? Okay, so what is the 15,000? Where did I come up with that number? These are the common machining operation. Let's take a look at the first one, right? Which is the drilling. That means, and if I talk about drilling, like when I talk about holes, like 2 hours, with 2 lectures of holes, and counterboards and counter sinks, like 2 lectures, we're talking about them. So I'm going to assume that you guys remember something about them. If I were to look at the drilling, and look at the type of tolerance that I can achieve, the biggest leeway, the biggest tolerance that I can achieve with this is 15,000. Why do I want 15,000? Because that means, unless otherwise specified, if I need to make a hole, this I can make it. Does that make sense? Now, if I have a special fit, I'm going to pull it out. Okay. We also talk about the rimming operation. Again, if you guys remember, the rimming is going to have a little bit higher tolerances. It's a secondary operation after the drilling. I can get 1.5, or let's call it 10,000, 10,000 so many, right? Now, when do I use rimming? Well, here I use rimming. What do I need rimming here? Because I want to make sure that things are going to be colliding, right? And I want to make sure that when I want to make the hole in the pin, they're really, really, really close to each other, so that when I expand it, I can put the pin. Does that make sense? Just dealing with a couple of thousands. Yes? Production tolerances. We can also have the lathe. We also have milling operations. Where's the lathe? Lathe, imagine yourself the drill that I usually show in the lectures. Kind of like a drill. This is the drill that makes holes, right? But it's a big one. Fast, right? And it has a spindle and it also has a chock. You just squeeze it like this. And then it just rotates, and from the side, you come and you cut material, right? So it will look something like this. Again, the big drill, this purple one right there. This is your stock pot, right? You go and you buy it, and then you grab your tool and it starts cutting material. Well, when you're cutting your part and you're trying to come up with a design, most likely you want to remove as much material as possible. And then when you get it really, really, really close to your design side with the tolerance that you're specified, you wanna slow down a little bit, right? Okay. Now I need to make sure that when I'm done, I just need to do a little bit more to finish the part. So the first operation, I took a lot of material. The finish operation, I just take a little bit, right? Barely touch the part so I can get a finished product. So you have roughing operations, you got semi-finished operations, and you got finishing operations. So when you guys are talking about the tolerance that I can achieve with this type of machining, this guy came about again, the 15 tau. Now, if I need something precise, the same way that I came up with the reamer, what do I do? Finishing cuts. That's if I were to use a lathe. I can also have a milling operation. What's a milling? Okay, I'm going to grab my drill before I grab it like this and I squeeze it. I'm going to flip it up and I'm going to go this way, go down. And I can make pockets, I can get contours and so forth, right? Guess what? You also have the same concept, right? You can also have roughing operations and finish operations. Now, what is the best that I can achieve with a milling? And again, you can also do a manual, or you can do the CNC programming. You program the tool paths, and that's for you, right? 5,000 in general. Now, what about if Ash came up with a super duper precise part? He's making something for his rocket ship, and he said, "Professor, oh, the machine is whoever is making it, right? I want my part to be 1.0000, 1.0000, and you come over here and then put a 1 right in there. So you go and you put it on the regular mill, and you give it 5,000, and then you come over here and you're like, oh shoot. That was the finished operation. I was only able to get 5,000, and you wanted 0.0001. So no enough, all right? Okay, so what's the next operation that I can do? I can put the grinder, right? Because the grinder is not going to take chips apart, it's going to be sparks of the part, right? So I'll be able to get 5 up to 10,000 of an inch, right? Am I there? No. Shoot, I really gotta go get my bazookas. So what I'm gonna do, I'm gonna put it on polishing compounds, buffing and lapping. Do the same way that you guys go and grab your cards and you buff it. It's just like this, man. Coach, we got 110,000, maybe we'll get that, right? So what do you think is gonna happen? Super expensive. So I'm gonna show you guys a video right before this so you guys have an idea of what I'm talking about. The more operations that you put, the longer it's gonna take to produce a part. The longer it takes to produce the part, the most costly it will be. In fact, the way they actually budget the machinist and the programmer is by the amount of time the machine takes to be produced, right? So let's say that you did 3 operations, and each operation took 3 times what it should have happened. And you still gotta go and have the setup, right? You can have the part and then flip it over, have the next setup, the next pulling operation go and do its own little thing. And they come up with the average time that it would take to do 1. And then they need to also guesstimate the time that it took you for you to grab in one part and put in the next part. Does that make sense? And then multiply that by 1,000. Right? So every little thing that you put will cost money. So the lesson of this is you make your tolerances as high as possible so that they can meet your function. And in our case, our biggest thing we can found in the it was 15 tau, right? You guys remember 15 tau is the magic number. You guys wanna learn it from this class? Learn the 15 tau. This is the rule. All tolerances should be given as large as possible without interfering with the function of the part in order to keep the cost down. Close dimensions are expensive. Now you don't know. You're like, oh man, I just became a designer, and they're making me go and come up with a spaceship. You ask your boss. You can either do 2 things. You can either do 2 things. You can give it a shot and 50-50, you might make it right, you might not make it right. And again, you gotta be careful when you go, you ask your boss, because if you ask him too many questions, he'll be like, why did I hire this? Right? Okay, let's talk about something else, tolerance stack-ups. And then I'll show you guys the video, okay? What is this tolerance stack-up? When you guys started mentioning, I told you guys baseline. From the bottom, from the left, from the back. Yes? Come up with a reference frame and start dimensioning from off of it. What you guys see here is a bunch of chain dimensions. If I were to look at each of the dimensions, I got 10 plus minus 5, 50 tau. 5 plus minus 50 tau, 50 tau, 50 tau, right? Well, in this case, it's millimeter. It's not 50 tau. You don't call millimeters taus. I don't know why. So you guys will notice that I went and I put the upper limit and the lower limit, upper limit and the lower limit on top and bottom. And then the question is, what would be I want to look at X and I want to look at Y. What would be the biggest X would be and the smallest X would be, right? So, which in this case would be the upper limit from X to Y. Is that correct? Okay. So if I were to look at this, let's say that I want to find out what is the biggest I can get. Come over here to whatever X is, and I want to say, okay, so if I want to make it bigger, I need to show that this guy goes this direction. Yes. And I need to show that this guy goes that direction. Yes. Okay. How would I do that? Well, if I want to find the maximum it could be from X to Y, I have to open it up. How do I open it up? By grabbing the biggest of this, the biggest of this, and the biggest of this. And I'm accumulating the biggest. Are we good? And if I want to go and I want to do the opposite, the smallest it can be, I should go the other way. Can see it? That way. That is what we're calling about the stack up, right? Because if you want to do this, you're accumulating tolerances. So your part actually continue getting bigger every time you have a dimension, right? And you most likely don't want this, right? Most likely you don't. Most likely you want to have a reference frame to dimension from, which in this case, what would that be? Baseline dimension. So if you are to look at baseline dimensions, everything starts from the baseline, right? Baseline. Now I still have the same question, though. My question is, what would be the biggest of these and the smallest of these? Same one. The previous one was much easier. This one's a little bit more tricky. Let's say that I want to do the biggest I can get. So I'm going to grab that one. I'm going to push it this way. I'm going to grab that one and I'm going to push it that way. Okay, so what is controlling this one? Well, this is controlling that one. Yes? How do I push it out? Let's grab the biggest one I can get. Right? And then this guy, what is controlling this line? Well, that guy is controlling that one. How do I push it towards the left? Well, it's the smallest it can be. Right? Grab this one, push it to the left. And grab this one, push it to the right. What is controlling this? Go off. What is controlling the bottom? And again, you will do the same concept if you want to do the minimum limit. You go the opposite way, right? Now, if you have a special function, though, then you call it out, right? Because remember, everything is unless otherwise specified. Maybe what you want to do is, you know what? By the end of my part, it doesn't matter where this piece of bracket is. From here to whatever feature that is, I want to have certain tolerance. Does that make sense? How do you do it? Just give it to them directly. No? Okay. Let me show you the video. So I can find the video.